A black hole could be hiding something that breaks the universe's rules. There's this problem in physics, the black hole information paradox. It's a direct clash between our two best theories, Einstein's gravity and quantum mechanics. Stephen Hawking said information, which is like the most basic thing in reality, gets erased inside a black hole. If that's true, then the universe is unpredictable at its core. Our physics would be built on a mistake. Solving this paradox is pushing us toward a completely new picture of reality. Space and time might not be what we think. We have to figure out how information could get out of a place nothing can escape. That's where ideas like firewalls and holograms come in. What happens to reality if a story, thrown into a black hole, is just gone? The universe is like a library, a cosmic library, and every atom, every photon is a book. A unique one. That's what information is in physics. It's the complete record. What a particle is, what it's doing, its position, its momentum, its quantum identity, and this library has one rule, a fundamental rule. Without it, science would fall apart. Nothing is ever checked out and destroyed. Information is never lost. It can be shuffled, translated, buried in a chaotic archive, but the original story persists. This principle of conservation means the universe is predictable. If you knew the exact state of every particle now, you could run the film backward. See the past or forward to see the future. John Archibald Wheeler had a phrase for this, it from bit. Every particle and force comes from a bit. A single unit of information. Reality is built from data, which leads to a terrifying question for the cosmic librarian. What happens if you take one of these books? The complete story of a star, a spaceship, a person, and you throw it into a black hole, a place where not even light returns. Is the library's rule broken? Does the story vanish from the record? To see why that's catastrophic, we need to look at the thing threatening to do it, the black hole itself. The black hole isn't just a threat because it exists. It's a threat because of its simplicity, its perfect featureless nature. The edge of a black hole is this contradiction. It's not a wall. It's more like a threshold in space and time. A line where gravity gets so strong that the idea of escape just stops meaning anything. Once you cross it, every possible path you could take bends inward. All of them toward the center. In Einstein's theory, that boundary, the event horizon, it's smooth. It's a one-way surface. You could float right across it, and in that moment you wouldn't feel a thing. No jolt, no rip. It's defined by a change in destiny, not by something you can touch. And that gives us the first clue. A disturbing one. For all their power, black holes are described by just 3 numbers. Mass, electric charge, spin, that's it. It's called the No-Hair Theorem. A black hole has no hair. It has no memory. Take a star of hydrogen and a star of iron. Collapse them into black holes with the same mass, charge, and spin. They become the same object. Indistinguishable. Throw in a grand piano or a library. Or a hard drive with every photo you own. From the outside, the black hole just gets a little more massive, spins a bit differently. All that intricate information, the specific arrangement of particles that made those things what they were, it seems to be erased. Wiped from the ledger, the black hole shows a blank face to the universe. It's the ultimate simplifier, reducing infinite complexity to 3 digits. This blankness was strange, but for a long time physics could accommodate it. Maybe the information was just locked away, trapped forever behind that one-way curtain. As long as it still existed somewhere, the fundamental rule was safe. But then Stephen Hawking looked closer, and he found that black holes aren't eternal. They're not silent. They whisper, and in that whisper he found the real paradox. That whisper is Hawking radiation. To understand it, you look at empty space. But space isn't empty. Even in a vacuum between galaxies, it's not still. At the smallest scales, there's constant motion, a quantum sea. Particle and antiparticle pairs flicker into existence. They borrow energy just for an instant, then annihilate, vanish back. It's a ceaseless dance, creation and destruction, everywhere all the time. In 1974, Stephen Hawking asked a question. What happens to this dance at the edge of a black hole, right at the event horizon, where gravity twists reality itself? He imagined a scenario. One of these particle pairs appears at that threshold. In the black hole's violent tug, the two particles can be torn apart. Before they destroy each other, one falls inward, past the point of no return. Its partner gets flung outward. Escapes. From the outside, it looks like the black hole emitted a particle. It glowed. And to pay for that energy, the black hole loses a tiny bit of mass. That's Hawking radiation, a slow leak, a thermal glow from the boundary. It was a monumental discovery. It meant black holes aren't forever. Over vast timescales, a black hole evaporates, particle by particle, until it winks out. But Hawking's calculation had a bombshell. He found this radiation was purely thermal, like heat from a lump of coal. Or the glow from a hot iron. Think of a hot stove. You measure its temperature from the infrared light. But that light tells you nothing about what the stove is made of. Iron or steel, part of a car or a skyscraper. The thermal radiation is generic. It carries heat but no story. Hawking argued the radiation from a black hole was the same. It carried energy away, but none of the specific quantum information about what fell in. The star, the piano, the library, all of it scrambled, trapped inside. And when the black hole evaporates to nothing, that information is gone, erased. Hawking stated it plainly. Information is lost in black holes. That declaration set the stage for a war. A conflict between two pillars of physics. On one side, quantum mechanics. Its ironclad law that information must be preserved. On the other, Einstein's general relativity, combined with Hawking's calculation, which said black holes destroy it. One theory had to be wrong, and figuring out which one would force us to rewrite reality itself. This is where our two great theories of reality finally meet. And they can't agree. They're like master architects, but one builds with stone and the other with light. Each blueprint is perfect on its own, but when you try to merge them at the edge of a black hole, they clash. General relativity gives us the stage. It's the theory of the very large, planets, galaxies. It describes space and time as a smooth, continuous fabric. When mass or energy sits on that fabric, it creates a curve, a warp. In this view, gravity isn't a force pulling you down. It's just you following the natural curve of the stage. At a black hole, the stage curves so steeply it forms a bottomless pit. The event horizon. Once something rolls in, the path only leads one way, deeper. The mathematics here is clean, deterministic, beautiful. It says if you know the starting conditions, you can predict exactly how everything will move. And it says information that crosses the horizon is gone from our universe, sealed away in a vault that eventually vanishes. Then there's quantum mechanics. The theory of the very small. Atoms, particles, its stage is nothing like a smooth fabric. It's a buzzing, probabilistic froth. Here, particles don't have definite locations until you look. They exist in multiple states at once. A ghostly superposition, and this theory has one sacred commandment. Information must never be destroyed. It can change form. It can become incredibly scrambled, but it must persist. The universe, in the quantum view, is a giant computation. It never loses a single bit. To lose information would make the past fundamentally unknowable. The computation would crash. For decades, these theories lived apart. Relativity ruled the cosmos. Quantum mechanics ruled the atom. They ignored each other. But a black hole is the ultimate intersection. It's an enormous object, born from a collapsed star, governed by relativity. Yet its defining feature, the event horizon, is a microscopic boundary. That's where quantum effects, like Hawking radiation, take center stage. This is where the architects are forced to work on the same building, and they're fighting over the blueprint. Relativity, with its smooth stage, says the horizon is a gentle threshold. Information sails through, unharmed but trapped. Quantum mechanics, with its demand for preservation, says that can't be the final answer. If the information is truly trapped in a vault that evaporates into random heat, then it's lost. The quantum commandment is broken. This is why Roger Penrose called it the most important problem. It's not a minor puzzle. It's a direct signal that our understanding of space, time, and reality is incomplete. We're missing the rulebook for when gravity and quantum effects meet. Solving the paradox means finding that rulebook. It means discovering the theory of quantum gravity, a framework that would weave these two magnificent, conflicting visions into one. To feel the weight of this, you have to ask what it truly means for information to be lost. It sounds technical, but the consequence is a universe that forgets. Think of a law, a guarantee. If a book burns, you could rebuild it from the ashes, literally. If you knew the position of every atom, every spark, every bit of smoke, you could reverse it. Watch the pages unburn, the ink return, the story restored. That's not magic. It's a rule in quantum mechanics, unitarity. It says any quantum process is reversible. Information isn't erased, it's rearranged. So from the final state of the universe, you could calculate every step that led there. The past isn't a mystery. It's written into the present. That's what makes science work. It makes the universe predictable, knowable. Now imagine that law failing, not bending. Shattering, that was Hawking's point. If information falls into a black hole and vanishes, then unitarity is broken. Reversibility is gone. The burned book is gone forever. Even with perfect knowledge, the ashes tell you nothing. The consequences spread. They warp the logic of reality. If information can be destroyed, then identical starting points could lead to different endings. Cause and effect, that backbone of how we understand things, begins to fray. The universe becomes unpredictable, not just complex but capricious. As physicist Leonard Susskind put it, if quantum mechanics is wrong about information conservation, then it's just wrong. Our most successful scientific framework, the one behind transistors, lasers, our picture of the atom, would have a fatal flaw. Vast realms of technology, our entire cosmic history, would rest on shaky ground. That was the crisis, a direct threat to the order of the cosmos. And with the crisis defined, the fight to resolve it began. The first major counterattack didn't come from tweaking equations. It came from a radical idea, one that stretched the imagination. It proposed that the most sacred surface in physics, the event horizon, might not be a gentle threshold. It might be a wall of fire. The firewall was a desperate move, a violent rewrite to save quantum mechanics, but there was another path, more elegant. It didn't destroy the horizon. It reimagined reality. It asked a question so strange it still echoes. What if everything we see is a hologram? That's the holographic principle. Its roots go back to black hole thermodynamics. In the 1970s, Jacob Bekenstein found a link. He said a black hole's event horizon has entropy. Entropy is a measure of disorder, of hidden information. More entropy means more possibilities. For a black hole, Bekenstein argued, this entropy is proportional to the area of its horizon, not its volume, its surface area. That was the first clue. In our world, the information capacity of a room depends on volume, how many books you can fit inside. But for a black hole, the ultimate container, the information limit is on its skin, on its two-dimensional boundary. Gerard T. Hooft and Leonard Susskind took that clue and ran with it. They proposed a radical idea. What if this isn't just a black hole quirk? What if it's a fundamental law? The holographic principle suggests all the information in any volume of space can be fully described by information stored on its boundary. A lower dimensional surface. Think of a hologram on a credit card, a flat, shiny sticker. But when light hits it, it projects a full three-dimensional image. All that depth, every angle, is encoded on that two-dimensional surface. The holographic principle says our universe might work the same way. The three-dimensional world we experience, with stars and planets and people, could be a projection. A cosmic illusion. The real data, the real code, lives on a distant, giant surface we can't see. For a black hole, that surface is its event horizon. Imagine the horizon not as a cliff edge, but as a vast, super-dense hard drive, composed of unimaginably tiny pixels, each one Planck length in size. That's the smallest possible length in physics. When an object falls toward a black hole in this view, it doesn't just vanish inside. Its information gets smeared out. Translated, encoded onto this shimmering, pixelated surface, like an intricate tattoo written in quantum bits. Later, as the black hole emits Hawking radiation, that information is slowly read back out. Emitted in the subtle correlations between the escaping particles. The story isn't burned. It's scanned, saved to the horizon's surface, and then printed out again, page by page in the evaporating glow. That transforms the entire paradox. Information is not lost. It never falls into a place of no return. It's just translated from a three-dimensional format into a two-dimensional one, and then back again. The black hole becomes an information processor, not a shredder. But this idea raises a profound question. How? How does the information of a three-dimensional object get painted onto a two-dimensional screen? What is the brush and what is the ink? The answer seems to lie in one of the most mysterious connections in the quantum world, a ghostly link called entanglement. That ghostly link is entanglement. Two particles can be born together, linked. Their properties become intertwined, spin, polarization. You separate them by light years, but measuring one instantly tells you the state of the other. It's as if they share a single existence. Albert Einstein called it spooky action at a distance. It seemed to violate his rule that nothing travels faster than light. But experiments have proven it's real. It's the bedrock of quantum computing, a connection that defies our intuition about separate objects. For decades, entanglement was seen as a weird property of particles. A mathematical correlation, but what if it's more? What if that spooky connection has a physical shape in the fabric of the universe? This leads to an idea. ER equals EPR. On one side EPR, that's Einstein, Podolsky, and Rosen, the paper highlighting the paradox. It represents the quantum link. On the other side ER. That's Einstein and Rosen, who worked on bridges in spacetime, wormholes. The conjecture proposes an equivalence. What if every instance of quantum entanglement is physically a microscopic wormhole? A tiny tunnel stitching the particles together through spacetime geometry. The spooky action isn't magic, it's architecture. You can't have the connection without the tunnel. They are two descriptions of the same thing. One in the language of quantum information, the other in the language of geometry. Apply this to a black hole. The Hawking radiation pair. One particle falls in, its partner escapes. According to ER equals EPR, those two are entangled, and that entanglement is a physical bridge. A microscopic wormhole connecting the particle inside to the one outside. This provides a potential escape route. Not for the particle which is still trapped, but for the information it carries. The information could traverse the wormhole. It could be transferred through these quantum threads to the radiation streaming out. The black hole's interior and exterior remain connected by a web of these tiny tunnels. This offers a geometric mechanism for information to get out. Nothing moves faster than light across the void. It's a solution written in the shape of reality. The implications are staggering. It suggests spacetime might not be fundamental. It might emerge, like temperature emerges from the motion of atoms. What if the fabric of space and time is woven from countless quantum threads of entanglement? If you took away the entanglement, the fabric would unravel. Space itself would dissolve. This idea points toward a framework where the event horizon isn't a destructive boundary, but a transformative surface. A processor built from the geometry of quantum connections, and it leads directly to the most ambitious attempt to solve the paradox, a theory that tries to build the universe from the ground up using information and connection. If the horizon is processing information, not just blocking it, Then it has to do that without breaking, and the answer seemed to be entanglement, but that answer created a new paradox. A much worse one, a wall of fire. In 2012, a group of physicists Ahmed Almeri, Donald Marolf, Joseph Polchinski, James Sully, they published a paper. It sent shockwaves. They took the holographic idea seriously. That information is stored on the horizon and gets out through Hawking radiation. They followed the quantum rules of entanglement. They followed them all the way to the end, and they found a contradiction, a severe one. It seemed to demand a physical firewall. Here's the problem. Think of the Hawking radiation as a stream of particles, pair by pair. For the information to be preserved, the radiation escaping now has to be linked, entangled with the radiation that escaped earlier. That's how the story gets pieced back together. But there's another link. The original particle pair at the horizon. The one that fell in and the one that flew out. They are born entangled. That's a fundamental quantum fact. So now you have a love triangle, a quantum love triangle. The escaped particle, call it A, is supposed to be entangled with its partner B, which fell in long ago. But for information to get out, particle A must also be entangled with all the older radiation C that came before it. Quantum mechanics has a strict rule, monogamy of entanglement. A single particle cannot be fully, faithfully entangled with two different things at once. It's not allowed. It would be like a secret code being perfectly decipherable in two completely different ways. The math breaks down. The AMP's paper laid out the logic. To save quantum mechanics, to allow information to escape, one of these entanglements has to break. Which one? They argued it must be the link between the particle just outside the horizon, A, and its original partner inside, B. That link has to sever. But in quantum theory, severing an entanglement isn't a quiet event. It releases an enormous amount of energy, a discontinuity. The consequence, at the event horizon, there would no longer be empty space. There would be a searing curtain of high-energy particles, a literal firewall. Anything crossing the horizon would not experience a smooth fall. It would be incinerated, vaporized in an instant. This was the paradox made flesh or made fire. It forced an impossible choice. Option 1, accept the firewall. This saves quantum information, but it destroys Einstein's equivalence principle. That principle is the heart of general relativity. It says if you're in free fall, like crossing an event horizon, you feel no gravity, you're just floating. There is no special surface. The firewall says that's wrong. The smooth horizon becomes the most violent place in the universe. Option 2, reject the firewall, keep the horizon smooth, but then the entanglement remains and you violate the monogamy rule. Which means the information cannot be faithfully encoded in the radiation. It is lost. And quantum mechanics, our most successful framework, is fundamentally flawed. Neither choice is acceptable. The firewall paradox wasn't a solution. It was a scream from the mathematics, a sign that our patchwork understanding had reached a breaking point. We couldn't just glue quantum mechanics and relativity together at the horizon. The conflict was now explosive. It showed that any answer would require something far more radical. Something that rewrites the rules of the game itself. The search was no longer for a tweak. It was for a revolution. The firewall paradox gave us two nightmares to choose from. But maybe that choice isn't real. Maybe the whole setup is wrong. That smooth event horizon, the perfect one-way membrane from Einstein's equations. What if it's not there at all? That brings us to a fifth idea. Fuzzballs and the end of smooth horizons. String theory tries to unify everything. And in that picture, the basic pieces of reality aren't points. They're tiny vibrating strings. When huge numbers of them come together, they can make exotic objects. Samir Mathur and others suggested a black hole could be one. Not a vacuum with a singularity at the center, but a giant, tangled ball of strings and membranes, a fuzzball. Think of a star, but instead of gas, it's a dense quantum knot. It has a surface, but that surface isn't a classical horizon of nothingness. It's the actual physical boundary of the fuzzball itself. It sits about where the horizon should be. But there's no empty space inside, no smooth curtain to cross. The interior is all fuzz, a complex, stringy structure packed with information. Now, something falls toward it. In the old story, it crosses the horizon and is gone. In the fuzzball story, it never finds an empty interior. Instead, it hits the fuzzball's surface. It merges with it. The information of the falling object, the specific arrangement of its particles, gets scrambled right away. It's woven into the vibrating strands of the fuzzball. It becomes part of the knot. That changes the information paradox completely. There's no mysterious interior where information gets trapped. The information is right there on the surface, woven into the object. So Hawking radiation doesn't come from pair creation at a vacuum boundary. It comes from the whole complex surface of the fuzzball. Because that surface is buzzing with quantum data, the radiation it emits naturally carries that information away. The story is imprinted in the subtle correlations between the particles. The paradox just evaporates because the cause, the classical smooth horizon with a vacuum behind it, was never real. It suggests black holes aren't like holes. They're more like the strangest stars you could imagine. They have a true physical structure, even if it's governed by the bizarre rules of strings and quantum gravity. The fuzzball idea sidesteps the firewall. There's no sharp horizon to host a wall of fire, because the horizon is replaced by a tangible, fuzzy surface. And it avoids information loss, because information is never sealed away in a geometric prison. This string theory view opens a door. If black holes are such complex objects, maybe information doesn't just leak out through Hawking radiation. Maybe there are other, more subtle ways, quantum echoes or minute tremors in spacetime itself. The fuzzball isn't a silent endpoint. It's a dynamic, vibrating thing. And in those vibrations, the universe might be whispering its deepest secrets, hinting at how information always finds a way to make its mark on the world outside. The idea is that information might not be stored in the knot itself, but on the wind, a whisper, something so faint it barely registers. That's soft hair. Think of the gentlest breeze. It doesn't move a leaf, but it could leave a pattern on the surface of a still pond. Ripples so small they're almost not there. Hawking, Strominger, Perry, they proposed black holes might have this soft hair, infinitesimally low energy excitations right on the event horizon, caused by gravitational waves or other fields from whatever falls in. These aren't big changes. They don't change the mass or the charge or the spin. They're described by mathematical symmetries, supertranslations. You have a perfect sphere. Now slide every point on its surface in a specific, smooth pattern. The sphere is still a sphere. Its essential properties are the same, but the surface coordinates have been shifted. That's a supertranslation, a gentle remapping of the horizon's geometry. So when something falls toward a black hole, it doesn't just vanish. It imparts a specific pattern of these supertranslations. It combs the soft hair in a unique way. And that pattern is a memory, a delicate imprint of what fell in. Information written in a script of almost zero energy. Later, as the black hole evaporates through Hawking radiation, this soft hair could play a role. The subtle geometry of the horizon, shaped by those imprints, might influence the radiation that leaks out. The information isn't carried by a single particle. It's encoded in the statistical correlations across the entire globe. It's a ballet of symmetries and memory. The story of the fallen object isn't burned. It's translated into the language of the horizon's gentle deformations, and then whispered back out, bit by quantum bit, over eons. Now, this idea is elegant. It's promising, but it's a frontier. The mathematics is profound and still being explored. It suggests the solution to the paradox might not be a violent firewall or a radical new object. It might lie in the most subtle of quantum gravitational effects, in the almost invisible ways that reality remembers. And if even the faintest breeze can leave a lasting mark, then perhaps nothing is truly forgotten. But information is written in such a subtle script. How do you read it back? The answer might be in a concept from computers brought into physics: quantum error correction. You're sending a message across a noisy channel. Static crackles, bits get flipped, zeros become ones. A simple code won't help, but a sophisticated error-correcting code can. It doesn't just send the message, it spreads it out. It entangles the original data with extra bits in a clever pattern. Even if parts are corrupted or lost, you can recover the original. By looking at the relationships between all the pieces, the whole story is greater than any damaged part. This isn't just for protecting data. Physicists like John Preskill and Patrick Hayden proposed something. Spacetime itself might operate like a giant, natural quantum error-correcting code. The black hole is its ultimate processor. In this view, when something falls in, its information isn't stored in one place. Not on a local hard drive at the horizon, not inside a Fuzzballs core. Instead, it gets spread out, non-locally. It's distributed in a highly entangled state across the entire system. The interior, the exterior, the Hawking radiation, all of it becomes one interconnected web. The information is everywhere and nowhere specific. It's like taking a document, shredding it, mixing the pieces with a mountain of confetti, and scattering that confetti across a continent. The words are still there, but finding them requires knowing the precise recipe of the scattering. Hawking radiation, then, isn't random heat. It's the output of this cosmic code. Each escaping particle carries not the story, but a single, scrambled piece of the story's blueprint. An observer far away, collecting enough of this radiation over the black hole's lifetime, could in principle run the error correction algorithm in reverse. Take all those scrambled pieces and reconstruct the original message, the book that fell in. But the reconstruction is a task of almost unimaginable complexity. It's not about grabbing one particle and seeing a picture. It's about painstakingly decoding the subtle quantum correlations between countless trillions of them. This aligns with the holographic principle. It views the black hole as a quantum computer of staggering scale. Its job isn't to destroy information. Its job is to perform the most complex encryption and error correction operation in the universe. The horizon is the screen where the computation happens. This transforms the paradox. It's no longer a question of if information gets out. The code ensures it does. The question becomes one of computational complexity. Can we, in any practical sense, ever actually retrieve it? The mathematics suggests that while the information is preserved in principle, decoding it might require more time and energy than the universe contains. It's technically possible, but physically impractical. The story is saved, but it's saved in a vault that takes longer to open than the age of the cosmos. This leads to a kind of pondering. If information is preserved but forever locked behind a wall of computational impossibility, what is its ultimate fate? Is a story that can never be read any different from one that is burned? The universe's ledger might be perfectly kept, but its pages could be written in a language too costly to ever translate. This computational angle doesn't just solve a physics problem. It asks what we mean by knowledge, by history, by reality itself, when the deepest truths are preserved yet perpetually out of reach. That computational vault might still be unlocked. The key was in a simple curve on a graph. Don Page looked at black hole evaporation as a story of entanglement. He asked a practical question. If someone outside collects the Hawking radiation, when does the information about what fell in become accessible? His answer was a specific moment. The Page time, it's the halfway point. Only after the black hole has lost about half its original mass does the radiation stop being pure random heat. Before that, the escaping particles are entangled with partners inside. They carry no decipherable story. They're just noise. But after the Page time, something shifts. The radiation particles start becoming entangled with each other. New particles escaping get linked to the old radiation that came out long before. It's in these subtle quantum links, these correlations across time, that the scrambled information is encoded. The outside observer now has a puzzle with enough pieces. The radiation transforms from a hiss of static into a faint, coherent broadcast. It's like a detective gathering shredded confetti for decades, and only after collecting a mountain of it do the fragments start fitting together. The story emerges from the hidden relationships between all of them. This was a conceptual breakthrough, but it left a geometric mystery. How, in the fabric of spacetime itself, does this information transfer happen? Where is the story physically located when it's half inside and half outside? The latest answer uses a new tool in quantum gravity. The mathematics describes quantum extremal surfaces. These aren't physical boundaries. They're abstract surfaces of minimal quantum influence, calculated by summing over all possible histories of spacetime. In the early life of a black hole, this surface sits just outside the event horizon. It defines what the outside observer can see. The interior is disconnected. It's an island of ignorance, but as evaporation passes the page time, something happens in the equations. That quantum extremal surface jumps. It plunges deep inside the black hole behind the horizon. The region it now encloses, this interior island, becomes mathematically part of the external quantum system. It's as if the territory of the outside observer's understanding expands to claim a piece of the interior. The information on that island is no longer isolated. Through quantum gravity, it's now considered part of the encoded data in the Hawking radiation. The island formula shows how gravity itself enforces the rules of quantum mechanics. Information is not lost. It's preserved through a dynamic reorganization of what we consider inside and outside. The event horizon becomes less of a stark wall and more of a fluctuating boundary. This is a monumental reconciliation. It takes Hawking's original calculation of thermal radiation and shows how, when you include the full quantum gravitational effects, that radiation inevitably develops the necessary correlations. Unitarity is saved. The cosmic library's rule holds. The equations show the information leaking out, precisely as Page predicted. It's a triumph. Yet this mathematical elegance leads to a personal question. What does this preserved information mean for someone actually crossing the horizon? If the story of your existence is safely encoded in the radiation outside, what happens to your own experience of falling in? The equations describe a saved narrative for the universe, but they are silent on the view from within. The equations show information being preserved. But you have to ask, preserved for who? That's the personal part of the paradox. It comes down to whose story is actually true. Take two friends. Alice is the astronaut. She decides to take a leap. She dives toward a black hole. Bob, her colleague, stays behind in their distant ship. He watches through his instruments. They're both physicists. They both trust the laws, but they're going to see two completely different things. From Bob's perspective outside, Alice's journey has a clear arc. As she gets close to the event horizon, her image slows, it reddens, it fades from view. He never sees her cross. To Bob, Alice's information. The quantum data that makes her Alice, it gets slowly radiated back out. In the Hawking glow, that process takes eons, and because of the firewall argument, Bob has to conclude something. At the precise point where she seems to cross, Alice hits a searing wall. High-energy particles. From where he's standing, she's vaporized. Her story ends right at the horizon. Her information is encoded in the radiation that escapes. Now switch to Alice. She's in free fall. According to general relativity, Einstein's theory, which has never been wrong, she feels nothing special when she crosses. No jolt, no flash of heat. The horizon isn't a physical barrier, it's a mathematical line. She passes it without a sensation. For her, the story continues. She sails smoothly into the black hole's interior. The singularity, the point of infinite density, that's in her future. That's where her physical journey will end. But from her point of view, she crossed the horizon alive. So who's right? Did Alice hit a firewall and burn up? Or did she float through unharmed? Both stories can't be true in one objective reality. But both are perfectly consistent within each observer's own frame. That's the observer dilemma. It's a paradox of complementarity, a concept from quantum mechanics. Like light being both a wave and a particle depending on how you measure it, reality at the horizon might have two complementary descriptions: Bob's from the outside, Alice's from the inside. Leonard Susskind argued both are correct, because no single observer can ever see both histories. Bob can never follow Alice in to check if she was vaporized, and Alice can never send a signal back out to say she survived. There's no cosmic referee to compare notes. The information about Alice in this view isn't lost, but it is duplicated. For Bob, it's in the Hawking radiation. For Alice, it's in her continued experience inside. That idea brushes against another rule, though. The no-cloning theorem. Quantum information can't be perfectly copied. So how can Alice's quantum state exist in two places at once, inside and outside the horizon? The potential answer is as strange as the problem. The duplication might be allowed because the two copies are permanently separated by a causal horizon. They can never be brought together and compared. In the quantum world, if you can never, ever check if a copy was made, then maybe it isn't a violation. Not in any operational sense. This observer-dependent reality shakes things. It suggests objective truth. A single timeline everyone agrees on might be an illusion. What's real depends on who's measuring it. The smooth horizon and the fiery horizon aren't contradictions. They're two faces of the same quantum reality, visible only from particular vantage points. To resolve the paradox, we might need to accept that spacetime itself isn't a fixed stage. It's emergent, a relational construct. Its properties, even the question of life or death at a horizon, depend on the observer. That doesn't make the universe arbitrary. It makes it deeply contextual. And if reality is this fluid at its most extreme edges, it forces a question. What other certainties might be up for reinterpretation? The universe might be more like a single tapestry, a densely woven one, with threads connecting everything, even across what seems like an impassable divide. Those threads are wormholes, but not the kind you fly a ship through. These are Euclidean wormholes. They appear in the mathematics of quantum gravity. They're theoretical bridges in the geometry of spacetime. And in the modern fight to solve the information paradox, they've become the heroes. To see how, you think of the path integral. It's a way of calculating quantum probabilities. A particle doesn't take one path from A to B. It takes every possible path at once. The final outcome is a sum over all these histories. When you apply this to gravity, spacetime itself gets to take all possible shapes. And in that sum, wormholes appear. Tiny handles connecting different regions. These aren't necessarily tunnels you could travel through in real time. They're shapes in the mathematical landscape, but their effect is profound. They create correlations. They allow information to be shared between points that are otherwise disconnected. Now, place this around a black hole. The great puzzle was always how information from inside gets out to the Hawking radiation. The wormhole answer is elegant. It doesn't have to travel out because it was never truly separate. A Euclidean wormhole can connect the interior of the black hole to the faraway radiation that escaped long ago. Through this geometric bridge, a link is established. The information in the interior and the information in the radiation become correlated, entangled. The wormhole is the physical picture of that spooky quantum connection. ER equals EPR, made real in the equations. This became the key to finally drawing the page curve. The graph that shows information being recovered. Earlier attempts using only quantum particles failed. The math kept saying information was lost. But when researchers included these wormhole geometries in the gravitational path integral, something changed. The calculation shifted. The new geometry, called a replica wormhole, dominated the sum, and when they computed it, the curve bent. It showed the information content of the radiation growing after the page time. Exactly as required. The wormhole topology had saved unitarity. It's a stunning realization. Space-time geometry is not a fixed, rigid stage, it's dynamic. It adjusts. When quantum mechanics demands that information be preserved, the very topology of space-time changes to make it happen. Gravity isn't fighting quantum rules, it's enforcing them. The Replica wormhole is like a cosmic circuit, completing a connection that must exist for the universe to make sense. This hints at something deeper. If the geometry of spacetime can change so fundamentally to protect a quantum bit, then perhaps spacetime isn't the foundation of reality. Maybe it's the other way around. Spacetime itself might be emergent, a kind of collective illusion that arises from a vast, underlying network of quantum information and entanglement. The wormholes aren't just bridges in space. They are the seams showing how the tapestry is woven. And at the edge of a black hole where the fabric is stretched to its limit, we can finally see the threads. The wormhole idea ties the smallest puzzles to the largest ones. The black hole paradox, it's not just about black holes. It's a template, a test case for when gravity and quantum mechanics meet at the extreme. And the most extreme place is the very beginning, the Big Bang. In a way, the Big Bang singularity is like a black hole running backward. A black hole is a point in space where matter crushes down to infinite density. The Big Bang is a point in time where everything explodes out from infinite density. Both are places where Einstein's equations break. Both are edges to our classical understanding. So if information has a crisis at a black hole's horizon, it must face a similar crisis at the start of time. Think of it this way. A black hole has an event horizon, a boundary between inside and outside. Our expanding universe has a cosmological horizon, a limit to what we can see, because light from farther out hasn't reached us yet since the Big Bang. And just as some theories say a black hole's information is encoded on its event horizon, maybe the information about the whole universe, its starting conditions, its first moments, is encoded on our cosmological horizon. The universe's birth certificate, written on its farthest visible skin. The implications are huge. If the black hole paradox is resolved and information is preserved, then it suggests the universe's own initial quantum state isn't lost. It's preserved, translated into the structure we see now. The galaxies, the cosmic microwave background, the laws of physics, they'd be the output of that cosmic computation. The story of creation would be saved, but flip it. If information can be lost in black holes, then it could have been lost in the Big Bang. The first moment would be a true eraser. A cosmic reset that wiped the slate clean before anything was written. If that's true, then our cosmic history is fundamentally unknowable. We could never trace things back to a true beginning. The universe would have amnesia about its own origin. Our quest to understand where we came from would hit a wall. That's why the paradox matters beyond the fate of astronauts. Its resolution shapes our theories of cosmology. It guides how we think about the multiverse. If our universe emerged from some prior state, like a bubble in a cosmic foam, did information flow continuously from that parent into ours? Or was it cut off? The black hole is our laboratory for asking that. It even touches the mystery of time's arrow. Why does time move forward? Why do we remember the past but not the future? The increase of entropy points the arrow. Understanding how information flows and is preserved is key to understanding why the past is different from the future. The low entropy, ordered state of the early universe is the ultimate starting point for time's arrow. If that information was preserved, the arrow has a clear origin. If it was lost, the very direction of time becomes more mysterious. So this abstract debate about bits and black holes is a central pillar of how we comprehend reality. It connects the microscopic quantum world to the grandest cosmic scales. Solving how information escapes a black hole isn't just a technical fix. It's a master key. One that could unlock the deepest secrets of our existence, from the first instant to the final fate of everything. The paradox isn't a curiosity. It's a beacon, shining a light on the hidden architecture of everything. That whole theoretical picture is built on math and imagination. But science needs evidence. Can we actually test any of this? Or is the information paradox just a thought experiment? We can't directly observe Hawking radiation from a black hole in space. Not now. The radiation from a typical black hole would be incredibly cold. It would be drowned out by the cosmic microwave background, the leftover heat from the Big Bang. It's like trying to hear a snowflake land in a hurricane, but we still try to experiment. If we can't study the real thing, we build a model. Physicists create analog black holes in labs. Not with gravity, but with sound or light. One method uses a Bose-Einstein condensate. That's a fluid chilled almost to absolute zero. In that fluid, you can create a flow that moves faster than the speed of sound in that medium. Think of a river flowing smoothly, then going over a waterfall. If you're in the water upstream, swimming slower than the current, you get swept toward the edge. That point where the flow exceeds the local speed of sound is a sonic horizon. Ripples in the fluid, which are sound waves, can't fight their way back upstream. They are trapped, like light in a gravitational black hole. And in experiments, researchers have detected the analog of Hawking radiation. Pairs of sound waves generated at that sonic horizon. One gets swept over the waterfall and its partner escapes. This doesn't prove Hawking radiation exists in space, but it shows the underlying quantum effect is real. It can be studied in a controlled setting. These lab-grown horizons let us probe questions about information and entanglement in a system that mimics the paradox. Another approach looks to the sky with new tools, gravitational wave astronomy. It heard the first chirps of colliding black holes. It's just beginning. Future observatories like the space-based LISA mission will listen for lower-frequency ripples in spacetime. Some theories predict that if a black hole's horizon isn't perfectly smooth, if it has a quantum structure, like a fuzzball, then the ring-down after a collision might not be clean. There could be faint echoes, like a bell with a complex internal shape, a subtle reverberation after the main gong. Searching for these echoes in gravitational wave data is a direct hunt for signatures of quantum gravity at the horizon. A smooth classical horizon would produce one specific tone. A structured quantum horizon might sing a more complex song. The search also extends to the oldest light we can see. The cosmic microwave background. It's a snapshot of the infant universe. Some theories suggest that if very small primordial black holes formed in the universe's first moments and then evaporated through Hawking radiation, they would have left an imprint on this ancient light. Mapping the subtle patterns in that background glow might reveal the faint fossilized whispers of those long-gone black holes. That could offer indirect evidence about how information behaved in their final moments. A definitive, direct test of the information paradox is still a future challenge, but these pathways, from quantum fluids in labs to gravitational echoes in space, are bringing the problem out of pure theory into the domain of empirical science. They turn the paradox from a philosophical debate into concrete questions we can aim our instruments toward. The hope isn't just for a mathematically elegant solution anymore. It's for a signal from the universe itself, a clue written in waves, sound, light, or space-time, telling us how reality keeps its ledger. The evidence points toward preservation. Information is saved, but this isn't just about a physics equation. It touches much deeper questions. What it means for the nature of reality. The answer to the black hole paradox could decide whether the universe is, at its heart, a story you can tell. If information were truly lost, the implications are staggering. The universe would be fundamentally unpredictable, non-deterministic. Identical starting conditions could lead to different outcomes. Cause and effect, the logical chain we use to make sense of everything, from a falling apple to a galaxy's birth, would have a crack in its foundation. The past wouldn't be perfectly inscribed in the present. You couldn't rewind the cosmic film even with perfect knowledge. History would be partly erased. This challenges the premise of scientific inquiry. Science is built on consistent, knowable rules, on experiments being repeatable, on the future being, in principle, calculable from the present. A universe that forgets undermines that entire project. As philosopher David Deutsch has argued, the preservation of information is linked to the very possibility of knowledge. If information can vanish, true knowledge about the past becomes impossible. We'd be living in a cosmos with inherent amnesia. But if information is preserved, as the math of wormholes and quantum error correction now suggests, a different picture emerges. A profoundly orderly one. It supports a view of a computable, holographic universe, a cosmos where every event, every interaction, every particle is encoded. Like lines in a cosmic script, this universe is deterministic in a specific quantum sense. Its future is contained within its present state, not as a predetermined fate, but as a vast computation unfolding. The entire history is preserved in the structure of the now. This is a universe that never loses a single bit. It remembers everything. That vision brushes against big philosophical speculations. The simulation hypothesis, for instance, which asks if our reality is a complex computation. A universe that preserves all information perfectly, that operates like a quantum error correcting code, has the architecture of a supremely advanced simulation. Its rules are the rules of information processing. Its preservation of data is a prerequisite for a coherent, renderable reality. It also touches questions about consciousness and perception. If reality is a projection from a two-dimensional boundary, as the holographic principle suggests, then our rich, three-dimensional experience is a decoded illusion. Our senses are interpreting a lower-dimensional data stream. That doesn't make it less real, but it reframes what real means. It suggests the tangible world of objects and space is an emergent property. Something that arises from a deeper layer of informational relationships. Ultimately, the resolution of the paradox shifts our role. If information is preserved and the universe is comprehensible in principle, we are not passive observers adrift in chaos. We are potential decoders. Our quest for knowledge, from an apple's fall to a black hole's edge, is the process of reading the cosmic code. We are piecing together the story the universe is telling about itself. The black hole information paradox stops being a narrow physics problem. It becomes a litmus test for the cosmos. Its answer tells us whether we live in a universe that is ultimately knowable. A universe with a memory, a story, and a structure we can, with patience and genius, come to understand. The cosmic code needs a physical language. Bits that aren't abstract bits that are vibrating strings. That's string theory. The basic ingredients of reality aren't point particles. They're tiny loops, and their different vibrations produce every particle and force we know. But for the math to work, these strings vibrate in more than 3 dimensions. They need extra dimensions. Dimensions curled up into tiny, complex shapes. Each possible way to fold and twist those extra dimensions corresponds to a different lowest energy state, a different vacuum that creates a landscape of possible universes, each with its own physical laws. Our universe, with its specific constants, is one valley in an almost infinite cosmic terrain. In this framework, black holes get a radical reinterpretation. They're not unique, simple objects defined just by mass, charge, and spin. What we call a black hole from a distance is actually an enormous collection of possible specific configurations. These are the black hole microstates. Think of a diamond and a lump of coal. From far away, they might look like similar dark objects, but their internal atomic arrangements are completely different. One is a crystal lattice, the other is a chaotic jumble. A black hole in string theory is like that. From afar, it looks like a single, dark, simple sphere. But up close, at the quantum string level, it can be in any one of a truly astronomical number of specific configurations, a particular tangle of strings and membranes. A specific quantum arrangement of those fundamental threads. Each distinct tangle is a microstate, and the key is, All these different microstates, when viewed from a large distance, have the same mass, the same charge, the same spin. They all look like the same classical black hole. So where does information live? It lives in which specific microstate the black hole is actually in. The story of what fell in the star, the library, the astronaut, determines the exact pattern of the strings. It picks out one specific arrangement from that colossal pile of possibilities. The information isn't lost. It's stored in the intricate quantum details of the strings and brains that make up the object. This is where the Bekenstein-Hawking formula for black hole entropy finds its home. Entropy is a measure of disorder, the number of ways a system can be arranged internally without changing its overall appearance. The Bekenstein-Hawking entropy is proportional to the area of the black hole's horizon. In the string theory picture, this entropy gets a direct statistical interpretation. The entropy is simply the logarithm of the number of possible microstates. It counts the different ways you can tie the quantum strings into a knot that, from the outside, looks like a black hole of a given mass. That number is unimaginably large, but it's finite. And its logarithm matches the Bekenstein-Hawking area formula. That was a monumental achievement. It provided a microscopic, quantum mechanical account of where a black hole's entropy comes from. It's not a mysterious property of the horizon. It's a count of possibilities. This transforms Hawking radiation. It's no longer a mysterious glow from a vacuum. In this microstate picture, the black hole is a hot, complex quantum system. Hawking radiation is the thermal emission from this system, just as a hot piece of metal glows. As it emits radiation, it very slowly transitions from one specific microstate to another. The radiation carries away energy, and the black hole shrinks, moving through its landscape of possible configurations. And crucially, the radiation is not random. It is subtly correlated with the specific microstate. Over an incredibly long time, by collecting the radiation, an outside observer could in principle deduce which microstate the black hole started in. It would be like trying to figure out the exact arrangement of a billion marbles in a black box by carefully measuring the heat and sound it gives off. Impossible in practice, but possible in principle. The information about what fell in is gradually revealed in the radiation, not destroyed. This is a concrete, mathematical realization of information preservation. The paradox of the simple, featureless black hole is resolved because the black hole was never simple. Its simplicity was an illusion of distance. Up close, it is the most complex object imaginable. A specific knot in the fabric of stringy spacetime. The information is stored in that knot. The evaporation via Hawking radiation is the slow untying of that knot, releasing the story it holds. In the vast landscape of string theory, the information paradox turns from a crisis into a triumph of theoretical consistency, showing how quantum gravity can account for the most enigmatic objects in the cosmos. The intricate knots of string theory, the delicate bridges of wormholes, they have to obey a deeper law. They can't let a story be rewritten, which brings us to a final safeguard. The chronology protection conjecture. Stephen Hawking proposed it, a cosmic rule against time travel, because when you talk about information escaping black holes through exotic geometry, you get dangerously close to breaking time. Think of a closed time-like curve. It's a path through spacetime that loops back on itself. A world line where you could, in theory, travel into your own past. This isn't just science fiction. Certain solutions to Einstein's equations, like rotating black holes or traversable wormholes, they mathematically permit these paths. They create scenarios where you could send a message backward in time, or even yourself, and that's where logic unravels, the classic paradox. You go back and prevent your parents from meeting. If they never meet, you are never born. But if you're never born, you can't go back to stop them. It's a contradiction. A logical inconsistency the universe, as a coherent system of cause and effect, shouldn't allow. Now connect this to the information paradox. Some of the most promising solutions involve wormholes, bridges connecting different points. If these bridges could be manipulated, stretched, they might not just transfer information from inside a black hole to the outside. They might connect 2 points in time, creating a shortcut to the past. If the mechanism that saves information from a black hole also accidentally creates a time machine, then you've solved one paradox by creating a far worse one. Hawking's conjecture is essentially a bet, a proposal that the laws of physics, quantum mechanics especially, contain built-in mechanisms that prevent closed time-like curves from forming, that any attempt to build a time machine will be thwarted. A quantum effect, like vacuum fluctuations, will become infinitely large right at the threshold of creating a time loop. It destroys the conditions needed. The universe, in this view, has a self-correcting code. It patches its own logical vulnerabilities. This places a huge constraint on any solution to the information paradox. It's not enough to show mathematically that information can escape. The proposed escape route must not, under any circumstances, become a tunnel to yesterday. The wormholes of the ER equals EPR correspondence, for example, they're likely not traversable in the classic sense. They're quantum bridges, useful for entanglement and information transfer, but they collapse if you try to send a physical object through. They're threads, not tunnels. This balance shows something about how theoretical physics progresses. A successful theory isn't just a clever fix for one problem. It has to satisfy a whole web of requirements. It must preserve information. It must respect quantum mechanics and general relativity. It must account for what observers see. And it must protect causality. Keep the arrow of time pointing forward. Each condition tests the solution from a different angle. A proposal that creates time travel is, in many ways, as unacceptable as one that destroys information. Both violate the consistency of reality. So the quest to understand black holes becomes a test of cosmic coherence. We're not just figuring out what happens to stuff that falls in. We're stress testing the logical fabric of the universe, asking if its rules can hold together under the most extreme conditions. The fact that we even have to consider chronology protection shows how intertwined these mysteries are. Information, black holes, entanglement, and time, they're not separate puzzles. They're different facets of a single enigma. Solving one means understanding how they all fit together in a way that prevents the universe from contradicting itself. The final answer, when it comes, will likely be a framework where the preservation of stories and the protection of time are two sides of the same unbreakable law. String theory has this grand vision, but it's not the only way to think about quantum gravity. There's another major idea that starts from a completely different place. Loop quantum gravity. It isn't trying to unify all the forces. Its goal is narrower, to take the rules of quantum mechanics and apply them directly to spacetime itself. In Einstein's picture, spacetime is smooth. It's a continuous stage. Loop quantum gravity says that at the very smallest scale, that stage isn't smooth. It's woven from a network of tiny loops. You can picture it like a fabric made of individual threads. These threads are one-dimensional lines of gravitational field. Where they cross, they create nodes, a spin network. That's the quantum geometry of space. It's not that space is made of something sitting inside space. Space itself is this evolving web of quantum connections. The fabric is pixelated. There's a smallest possible area, a smallest possible volume, a fundamental graininess to reality at the Planck scale. And this granular structure changes what happens at the end of a black hole. In some loop quantum gravity models, when a black hole evaporates through Hawking radiation, it doesn't disappear entirely. It leaves behind a remnant, a tiny, incredibly dense knot of spacetime geometry, a stable object with a mass around the Planck mass. It's a minuscule speck, but it holds the gravitational memory of everything that ever fell into the original black hole. The information isn't carried away in the Hawking glow. It's trapped inside this final, indestructible vault. So the paradox is solved because the information never actually leaves the universe. It's just locked in a permanent, microscopic tomb. But that solution creates a new, profound puzzle. If every black hole that ever forms leaves one of these remnants, and black holes can form constantly across cosmic history, then the universe should be filling up with an infinite number of them. An ever-growing sea of Planck-scale data tombs. That's a problem for cosmology. It also raises the question of infinite information density. Could the universe store an unlimited amount of information in these tiny specks? The physics of that kind of infinite production is deeply troubling. It suggests the remnant idea might just be trading one paradox for another. Beyond string theory and loop quantum gravity, there are other frameworks looking at the quantum geometry of spacetime. The idea of asymptotic safety proposes that gravity might be a consistent quantum theory on its own, without extra dimensions or strings, if its strength changes with scale in a very specific way. Near a black hole, this could smooth out the singularity and change how information is processed at the horizon. Another approach, causal dynamical triangulations, builds spacetime from simple geometric building blocks, like tiny triangles or tetrahedra, glued together. It lets the geometry of a black hole emerge from the collective behavior of these blocks, which could show how information might flow through a quantum foam without being lost. What's remarkable is that all these vastly different roads, strings, loops, triangles, they all have to pass through the same gate, the black hole information paradox. It's the ultimate benchmark. Any candidate for a theory of quantum gravity isn't truly viable unless it can naturally, elegantly explain how information is preserved. The solution can't be tacked on as an afterthought. It has to emerge from the theory's core principles. This forces a beautiful discipline on theoretical physics. All this wild mathematical creativity gets funneled through the narrow, unforgiving test of a black hole's fate. The paradox isn't just a problem to be solved. It's a crucible, a refining fire that burns away inconsistent ideas and reveals which mathematical structures might actually describe our universe. This diversity of thought, this competition of frameworks, it isn't confusion. It's the sound of a field alive with possibility, driven by one of the most profound questions we've ever asked about the nature of reality. The fact that we're even asking about this paradox, that might be a clue in itself. We're here, conscious, made of complex structures. We can observe things, use logic. The Anthropic Principle asks something pretty simple and pretty deep. What if the laws of physics we measure aren't the only ones possible? What if they're just the laws that allowed us to be here to measure them? Take that idea to the information paradox. Picture a multiverse. A vast cosmic landscape, maybe infinite universes, each with slightly different constants, different rules. In some of those universes, information might be lost in black holes. Unitarity breaks, cause and effect get fuzzy. Predictability just dissolves. In a universe like that, could stable structures ever form? Could planets coalesce over billions of years? Could that long, delicate chain of chemical reactions that leads to life ever find a consistent footing? It seems unlikely. A cosmos where information isn't preserved is a cosmos of fundamental chaos. The reliable patterns you need for stars, planets, observers, they might never emerge. Now, in other universes in this multiverse, information is preserved. The cosmic ledger is perfectly kept. Black holes become ultimate information processors, not shredders. In those universes, the laws are stable, predictable. They allow complexity to rise. We're here asking questions about black holes, so we would necessarily find ourselves in one of these orderly universes. Our existence isn't just a random fact. It's data, evidence pointing toward the kind of cosmic rules that permit existence. From that angle, the resolution of the paradox might not be a purely mathematical certainty from first principles. It could be an environmental fact. We live in a universe where information is conserved, because only in such a universe could creatures capable of noticing the paradox ever evolve. That connects the fate of information in a black hole to the deepest conditions for life itself. It ties quantum foundations to cosmology in a deeply personal way. The answer to whether a story is burned or saved becomes linked to the possibility of anyone ever being around to read it. This is speculative, philosophical. But it's a powerful reminder. The black hole information paradox isn't just an abstract puzzle for physicists. It sits at a rare intersection, where the mathematics of spacetime meets the logic of quantum theory, and where both meet the mysterious preconditions for a universe that can know itself. We aren't just external observers of this drama, we're products of its resolution. Our quest to solve the paradox is the universe attempting to understand its own foundational rules. Rules that had to be just so for the question to be asked at all. That perfect shuffle is called quantum scrambling. In a black hole, information doesn't just sit there. It gets mixed violently, perfectly mixed. A black hole is nature's ultimate quantum computer, and its main operation is chaos. Not random chaos, but a deterministic, hyper-fast mixing of every bit of data that falls in. The scrambling is so efficient that within a tiny fraction of a second, the specific story of a fallen star becomes inseparable from the total quantum state of the black hole. It's like taking an ordered library and instantly turning every letter of every book into a single, uniform soup. But no letter is destroyed. The information is preserved, but its meaning is hidden in a web of correlations so complex it looks random. The speed is mind-bending. For a stellar mass black hole, theoretical calculations say information could be scrambled in microseconds. This timescale is linked to the black hole's temperature. A hotter, smaller black hole scrambles faster. Physicists describe this with tools like out-of-time order correlators. These are mathematical measures that track how quickly a local disturbance, a single bit of information, spreads to become a global property of the whole system. In a black hole, these correlators decay exponentially fast, which is a hallmark of quantum chaos. It's the difference between a drop of dye diffusing slowly in water and that same drop instantly coloring the entire ocean. The black hole is the ocean. This changes how we see the horizon. It's not just a boundary, but the site of the universe's most intense information processing. The scrambling happens at or near this surface, encoding data onto the quantum degrees of freedom there. This rapid mixing is why Hawking radiation initially looks like random thermal noise. The information is there, but it's been scrambled into the subtle quantum entanglement between the escaping particles. To decode it, you wouldn't look at one particle. You'd need to measure the intricate relationships between all of them, a task of astronomical complexity. The implications go beyond astrophysics. The mathematics of black hole scrambling is similar to the behavior of certain complex quantum systems here on Earth, like strange metals or chaotic quantum dots. This has built a bridge between quantum gravity and condensed matter physics. Researchers now build tabletop experiments quantum simulators using cold atoms or superconducting circuits designed to mimic this scrambling behavior. They're creating laboratory models of event horizons to watch information spread and become entangled in a controlled setting. These aren't black holes, but they obey similar quantum rules, letting us test the foundational ideas on a lab bench. This work is more than theoretical. It's driving the frontier of quantum information science. Understanding scrambling is crucial for building fault-tolerant quantum computers, where controlling information spread is key to preventing errors. The black hole, the ultimate scrambler, has become a teacher. Its paradoxical nature is guiding us toward a deeper understanding of chaos, complexity, and how information shapes reality. In its terrifying efficiency, we find a universal principle, written in the language of quantum entanglement. Stephen Hawking and James Hartle asked about the quantum state of the whole universe. Their answer was the no-boundary proposal. The Big Bang wasn't an explosion from a point. It was a smooth, rounded geometry, a sphere with no edge. If you rewound time toward the beginning, the universe wouldn't hit a sharp boundary. Time itself would become more like a direction in space. The four-dimensional fabric of spacetime would close on itself. Like the surface of a ball, there is no before. Because there is no boundary to cross, The universe just is, a self-contained quantum entity. It arises spontaneously from the possibilities in the laws of physics. In that kind of cosmos, the question of initial information changes. You don't ask what information was present at the start, because there is no start, not in the classical sense. The information content of the universe is encoded in its entire geometry. Its seamless geometry. Now take that same quantum cosmological thinking and apply it to a black hole. The paradox makes us pick a side. Does information fall through the horizon, or does it hit a firewall? But step back. Consider the entire life of the black hole. From its violent birth to its quiet evaporation, as one single quantum object, a complete history in spacetime. The techniques are similar. They're like the Euclidean path integrals that gave us replica wormholes. You sum over all possible shapes this complete spacetime could take. In that sum, the sharp, singular point at the center of the black hole, and the moment of its final evaporation, they aren't treated as special boundaries. They are just parts of a larger, smooth manifold. The geometry can be contorted. It can connect the interior to the exterior through complex, non-classical paths. The distinction between inside and outside becomes fuzzy, not just in space, but across the entire timeline of the object. In this holistic view, the information paradox might simply dissolve. It was a problem born from trying to split the story into pieces. Before the horizon, after the horizon, during evaporation. But from the perspective of the complete quantum spacetime, information isn't passing from one region to another. It's woven into the topology of the entire manifold. The story of what fell in is preserved in the global structure of that spacetime, just as the story of our universe might be encoded in its no-boundary wave function. There's no need to specify what happens at the singularity, because the quantum description smooths it out. The information has nowhere to be lost, because the entire history is a single, self-consistent quantum state. This is perhaps the most profound unification. It suggests the fate of information in a black hole, and the origin of information in the cosmos are two aspects of the same question. Both are about boundaries or the lack of them. A black hole's event horizon and the Big Bang singularity both challenge our notions of before and after. The no-boundary proposal for cosmology and the smooth quantum histories for black holes both use the same mathematical tools to erase those problematic edges. In this grand vision, the universe and its most mysterious creatures are not separate puzzles. They are different expressions of a single, coherent quantum reality. A reality where every story finds its place, from the birth of the cosmos to the whisper of an evaporating black hole, in an unbroken, boundless whole. The conflict over the paradox was so intense it got a name, the Black Hole War. It wasn't a war with weapons, it was a war of ideas. It went on for decades. It was fought in papers at conferences, in public debates. On one side was Stephen Hawking. He was defending his calculation that information was lost for good. On the other side was a group, Leonard Susskind, Gerard T. Hooft, John Preskill. They believed the universe couldn't forget. The stakes were the foundations of physics itself. The debate was passionate. It got personal sometimes, and it was always profound. It showed something true about how science actually moves forward, not through quiet agreement. Through loud disagreement, rigorous disagreement, often uncomfortable disagreement, progress happens right at the edge of what we know, and that edge is a place of friction. This was a paradigm shift happening. An established view, held by a brilliant mind, was facing a revolutionary challenge. The whole community had to pick sides. They had to scrutinize every assumption. They had to invent new mathematical tools just to defend their positions. This was physics at its most dynamic. And its most human. At the heart of it were famous bets. In 1997, Hawking and Kip Thorne bet John Preskill. They bet that information was swallowed and destroyed. The wager was an encyclopedia of the winner's choice, where you could retrieve any information you wanted. It was a playful metaphor. And a pointed one. For years, it looked like Hawking was winning. His arguments were formidable: the smoothness of the horizon, the purity of the Hawking radiation. But the opposition kept working. Susskind championed the holographic principle. He said information was painted on the surface of the horizon. String theory developed. They counted black hole microstates. That gave a picture, a microscopic picture, of how information could be stored. The pressure kept building. Then in 2004, at a conference in Dublin, Stephen Hawking did something remarkable. He conceded. He said he had been wrong. Information could escape a black hole. He presented a new calculation. It used the Euclidean path integral approach. It suggested information could leak out through subtle topological changes in the geometry of spacetime. He gave John Preskill his encyclopedia, a baseball encyclopedia to be precise. That concession was a monumental moment. It wasn't a defeat for Hawking. It was a victory for the scientific process. One of the greatest minds of the century changed his position. Publicly, based on evidence, based on the persuasive power of new ideas, it showed the essential humility of science, its self-correcting nature. The black hole war offers a lesson about discovery. This wasn't a clean march toward truth. It was messy, iterative, driven by strong personalities. The resolution didn't come from one genius having a sudden flash. It emerged from a global conversation, physicists arguing over coffee, writing papers that challenged each other, building on fragments of insight from different fields. String theory, quantum information, gravitational physics. Take the Firewall Paradox. That wasn't a setback. It was a necessary crisis. It forced everyone to see their old assumptions weren't enough. It pushed the whole field toward more radical ideas. Ideas like Replica wormholes. The war shows that collaboration in science isn't just about working on the same team. It's about engaging with your most thoughtful critics. The most productive collaboration can look like fierce opposition, because it stresses ideas. It stresses them until they break or prove they're strong. This human story behind the paradox reminds us, science is a social endeavor, a creative endeavor. The equations and theories don't exist in a vacuum. They're born from curiosity. They're shaped by debate. They're refined through a shared commitment to understanding. This decades-long struggle to understand information in black holes is a testament to that process. It shows that even our most abstract questions about reality are pursued by people. People who get excited, who argue, who make bets, who have the courage to say they were wrong. The resolution of the paradox, whenever that final chapter gets written, won't belong to one person. It will belong to the whole community. The arguing, wonderful community of inquiry that took on a universe that seemed to contradict itself. Explaining this is a huge challenge. You have quantum mechanics and gravity in conflict. It's a problem of information and spacetime. How do you make that feel real to someone who isn't a physicist? That's where science communication becomes an art. It's translation, finding the right analogy, the right metaphor, to build a bridge from abstract theory to human experience. Educators and communicators have met this with real creativity. They don't water the ideas down, they find new ways to light them up. A black hole isn't just a cosmic vacuum cleaner. It's a holographic printer. It takes a three-dimensional object, scans its information onto a two-dimensional surface, the event horizon, and then slowly prints it back out into the universe as Hawking radiation. That simple image captures the holographic principle. It turns a dizzying mathematical concept into something tangible, almost familiar. Visualization is another tool. Virtual reality simulations let people experience the warping of spacetime around a black hole. You can fly toward an event horizon. You can see how light bends and distorts. You can watch a star get stretched into a stream of plasma. These aren't just cool visuals. They're experiential learning. They build an intuitive sense for the geometry that underlies the paradox. When you see with your own eyes how a horizon is a one-way surface in the fabric of reality, the stakes of the information debate get clearer. It's no longer about equations. It's about what happens at that threshold you just virtually crossed. Science centers and planetariums create interactive exhibits. They might use a flowing stream of water to demonstrate a sonic black hole, showing how ripples can't escape a certain point. They use large, tactile models to show how information could be scrambled and preserved. These hands-on approaches make the science democratic. They put the mystery directly into the public's hands. This outreach does more than explain. It inspires. A child seeing a simulation of colliding black holes, or a teenager grasping quantum entanglement through a simple card game analogy, might be the physicist who one day solves the next great paradox. By making the topic accessible, you plant seeds of curiosity. They can grow into a lifetime of discovery. The effort to communicate this also forces experts to clarify their own thinking. If you can't explain your idea in simple terms, do you truly understand it? The process of creating an analogy for a general audience often reveals hidden assumptions. Gaps in logic. It's a refining fire for the ideas themselves. Public lectures, popular science books, social media threads where scientists engage directly with questions. They all create a vibrant, living dialogue about the universe. That dialogue underscores a vital truth. The pursuit of understanding the cosmos isn't a remote activity for a select few in ivory towers. It's a shared human adventure. It lives in the questions of a student, the wonder of a museum visitor, the late-night conversation sparked by a documentary. When you break down a problem as profound as the black hole information paradox into relatable concepts, you do more than educate. You empower. You invite everyone to appreciate the depth and beauty of the mystery. You affirm that the desire to know how the universe works and to tell its story belongs to all of us. The holographic picture gives us a powerful framework, but it's not the final word. We have a map, and the territory still holds mysteries. Is the holographic description of black holes complete? Does it capture every nuance of quantum gravitational reality? Or is it an approximation? A brilliant one, but maybe something that gets absorbed into something deeper later on. We don't yet know how to take the elegant mathematics of information on the horizon and translate it, in practical terms, into a step-by-step account of how a story reassembles itself from the Hawking glow. The equations show it's possible in principle, but the devil is in the details of that emergence. The deepest insights are there in those details, and what awaits at the very end. After the last whisper of Hawking radiation, what is left? A stable, microscopic remnant, a tiny knot of spacetime holding all the original information in permanent quarantine. Or pure nothingness, a vacuum where a massive object once warped the cosmos, or something stranger entirely, a transition to a new phase of spacetime we can't yet imagine. Each possibility carries profound implications for the consistency of physics, for the ultimate fate of information. These questions point to a grander goal. Can we move beyond patches and approximations to formulate a complete, non-perturbative theory of quantum gravity? A framework that doesn't just work when gravity is weak or quantum effects are small, but one that holds firm in the violent heart of a black hole. From first principles, this is the Holy Grail, a theory where information preservation doesn't happen because we engineered it to, but where it emerges naturally, inevitably, from the core logic. The path forward will be interdisciplinary. We'll see deeper alliances with quantum information theory, treating spacetime not just as geometry, but as a quantum computational network. Advanced mathematical tools will be essential, from differential geometry and topology, to describe the intricate shapes of replica wormholes and quantum extremal surfaces. Unexpected insights may arrive from distant fields, condensed matter physics, where exotic phases of matter show holographic properties, or computer science, which grapples with the limits of complexity and decryption. The black hole information paradox was once seen as a threatening inconsistency. Now it's transformed into one of theoretical physics's most fertile grounds, It's a proving ground, a source of inspiration, and a compass. Every attempted solution, every new contradiction, forces us to refine our questions, to invent new mathematical languages. The promise is immense. Solving it won't just tell us what happens to information swallowed by a black hole. It will illuminate the fundamental architecture of reality itself. How space, time, and quantum information are woven into a single, coherent whole. The journey is far from over. In many ways, guided by this paradox, it has only just begun. From that stark idea of information being lost, we've come to a universe that remembers. The black hole information paradox was this terrifying crack in physics. But it's changed. It's not a flaw to fear anymore. It became a guide, a light that made us look deeper, to weave together general relativity and quantum mechanics into something richer. We went through ideas that felt like science fiction holograms with information painted on a surface, wormholes that are threads of entanglement, space-time emerging from a quantum code. These aren't just fixes, they're glimpses of a new synthesis. John Preskill said we've learned space-time isn't a static stage. It's a dynamic participant. A living geometry that bends and adjusts to protect every bit of information, every story, from being erased. This resolution is a victory for the scientific process. It shows that through curiosity and debate and relentless inquiry, we can face even the most daunting puzzles. The paradox didn't break our laws of physics. It revealed how they're truly connected. Every black hole mystery we solve, from the fate of information to the origin of spacetime, lights up another piece of the cosmic story. It reminds us the universe isn't just silent forces. It's a coherent narrative, written in quantum bits and gravitational waves.